All right, so we're gonna run through lesson 6 and 7. I'm gonna, go over this again tomorrow, but I need you to watch the video, get the basic ideas there. So the only thing that's really going to be relatively new that we're talking about is end behavior. We've mentioned multiplicities and talked about that, and then of course we're going to just try to put all that together to sketch graphs. And so just remember with multiplicities, depending on the multiplicity, if the multiplicity is a 1 or 2 or a 3, that determines how the graph crosses through the x-axis. So if it's a multiplicity 1, then the graph is going to cross straight through the x-axis. Nothing funny. Just going to go straight through. Multiplicity 1, multiplicity 1, multiplicity 1. Okay, nothing funny. If the multiplicity is 2, it's going to bounce off the x-axis. Bounce off the x-axis. Or it could be on top. It doesn't matter. If the multiplicity is 3, it's going to kind of flatten out and then go through. It's not a good graph of it, but you get what I'm trying to do. That's a multiplicity 3. Anytime it does something like that, that's a multiplicity 3. Okay? And so that's kind of what we're looking at when we talk about multiplicities. Okay? So those types of things. All right. End behavior just basically refers to what is happening at the end of the graph. Is the graph pointing up? Is the graph pointing down? But then there's a notation that you have to write with it. So every year I have students that will just write the words up or down, and I'm like, no, that's good that you understand that, but it has to be written in a certain notation. So when we talk about the graph, we talk about the left side of the graph and we talk about the right side of the graph. What's happening there? So for this function, this is not a polynomial function, but all graphs have an end behavior. So if you graph it, it has an end behavior. It's approaching something. Now, for this function here, because it starts to flatten out at y equals 4, this graph actually has an end behavior that approaches the number y equals 4 because of that. It flattens out there. It has a horizontal asymptote. So the way you would write that for the left side is we're saying that y values are approaching the number 4. So y approaches 4. But then the way that you would write that is you would say as x goes to negative infinity. What that means is as we go to the left to negative infinity, what is the graph doing? Okay, so as we go to negative infinity on this axis, the graph flattens out towards y equals 4. So we're going to say y approaches the number 4. Now, the right-hand side of the graph, as the graph goes to the right, so as I go this direction to infinity, what is this side doing? Well, this side is going up. So that means y approaches infinity. So as x approaches positive infinity, so as we go to the right, y approaches positive infinity because it goes up. That's all that is. That is the notation for end behavior. Same thing down here. Okay, and then all we do is we put that together. Okay, so looking at these graphs, so what we're going to do is we're going to look at two sets of graphs and we're going to try to compare them with end behavior and stuff. So there's some things when you're looking at the function only, you should be able to tell the end behavior. You should. And so your homework tonight is going to be about that. Like if you're looking at a function and then sometimes you will have a graph, which if you have a graph, the end behavior is easy because you just look at the arrows or the sides of the end of the graph or whatever. But if you have just the function, how can you tell the end behavior? All right, so it starts with the sign of the leading coefficient. So our leading coefficient for this is positive 1. So our sign is positive. And so once we have the sign of our leading coefficient, that lets us know what the right side of the graph is going to be doing. So when the leading coefficient is positive, the right side points up. So if I look here, that side's pointing up, this side's pointing down. But this side here is pointing up. That is the key. If I look over here, the sign of the leading coefficient is negative. Because we have a -1 in front of that there. So that leading coefficient is negative, so the right side points down. And so that's what that is. And so that takes care of at least how do I know like something about the arrows. All right, but then some of you are saying, well, the other side is pointing down though. Like, how do we know that? All right, well, that goes into the degree, and we're going to compare that in a little bit. So here we got the degree 3 because of the exponent is 3. Here, the highest exponent is 5. This is a degree 5 polynomial. Okay, now in behavior wise, as x goes to negative infinity, so as we go this direction, this is pointing down. As we go to the right, this side is pointing up like we already said. So infinity. Now, usually when I do in behavior, I always do the right side first because I know that side follows the leading coefficient. So if I was to do the one on the left, this right graph right here, the x to the fifth, I would start with the right side. So as x goes to infinity, because there's a negative leading coefficient, I already know that this side's going to point down. So I can say as x goes to the right, this side points down. But as x goes to negative infinity, then the side's pointing in the opposite direction. We'll change these to red real quick, just so they stand out. All right, so there's my in behavior. Okay, on the next slide, we have a couple graphs, but let's look at their stuff. So here, the sign of the leading coefficient is negative, but we see how the right side points down. Because again, it follows the leading coefficient. Here, the leading coefficient is a positive, and so we see the right side points up now. The degree is 2. Here, the degree is 2 as well. Now, the right side points down for this one. So as x approaches positive infinity, so as we go to the right, as we go this direction, this side points down. And then as we go to this direction, this side points down as well. And so negative infinity, and this side's negative infinity as well. And then on the other graph, they both point up to infinity because of the arrows. As we go to the right, this side points up. As we go to the left, this side points up. That's all this says. That's your in behavior. Okay, but again, how can we tell what's going to happen? Just by looking at the graph or the function without having the graph in front of us. So comparing these two slides, okay, we already talked about leading coefficient determines the right side of the graph. But what about the left side of the graph? Well, that depends on the degree of the function. If you notice here, these degrees are both odd. Oops. These degrees are both even. If the degree is even, both arrows will point in the same direction. If the degree is odd, they point in opposite directions. So that's how you can determine what the left side does. The right side of the polynomial always follows the leading coefficient. So when you're given a function, you know what the leading coefficient is. It's either going to be a positive number or a negative number. If it's positive, the right side automatically goes up. If it's a negative, the right side automatically is going to go down. With that knowledge, then I look at the degree. If the degree is odd, that means the left side is going to go in the opposite direction. So when the degree is odd, the arrows are going to point in opposite directions. All right, so I got this little graphic here to try to organize that thought. So if I look at this graph, I see that the arrows point in opposite directions. This side's up and this side's down. So this lets me know it's odd. Arrows point opposite. And then the leading coefficient I know is positive because even though I don't have a function in front of me, the right side is up. So it's a leading coefficient that's positive. So the end behavior, let me put this real quick. Here the right side is up. So that lets me know that that's leading coefficient is positive. So when I write my notation, as x goes to the left, and then typically what I do is I write the notation out in a shell form, like I basically just lay out the general notation first. So I just put these because these mean left and right, right? So as x goes to negative infinity, which is left, as x goes to infinity, that's the right side. The function f of x, now I'm using f of x, you can use y, it doesn't matter. And then all I'm going to do here is fill in the blank. So the right side points up automatically here, so I'm going to start with that one. Again, this is the right side because it says as x approaches infinity. That's the right side. And then this is the left side because x is going to negative infinity. So then you would say, all right, so since the right side points up and this is odd, the left side is going to be pointing down, which it does. If you look over here, we have another odd function because the arrows point in opposite directions. But the leading coefficient is negative this time because the right side points down. So as we do the end behavior, we're going to say as x approaches negative infinity on the left, and then as x approaches positive infinity on the right, what is happening? Well, the function approaches negative infinity on the right side because of the negative leading coefficient. The left-hand side is going to point to infinity. And then when they're even, it's just, you see how the arrows point in the same direction. Okay, and so the leading coefficient in this case is positive because you look at the right side and it's up. The end behavior, so as x approaches negative infinity on the left, as it approaches positive infinity on the right, f of x approaches something. In this case, because the leading coefficient is positive, I know that the right side is going to approach infinity. And then I know that this right side or left side is also going to approach infinity because both arrows point up. Okay, over here, the leading coefficient for this one is negative because I'm looking at my graph. I see that the right side is down. So as x approaches, I know I got all these colors here, but as x approaches infinity, so again, the left side and the right side, the function approaches either infinity or negative infinity. And so the right side is pointing down. So this side is also pointing down. When it's an even function, the arrows will always point in the same direction. So what I did here, this graphic organizer, is I just kind of put this together to show that you start with your degree. If your degree is even, then it lets you know that the arrows point in the same direction. If it's odd, the arrows point in opposite direction. So the arrows are in the same direction. Here, arrows are in opposite direction. Okay? And now, some of you saying, well, how do you know if it's even or odd? Well, if it's in standard form, you just look at the biggest exponent. When it's in factored form, you have to add up the multiplicities. Okay? And so, for example, if I have f of x equals this, the multiplicity is the exponent. So here, this is a multiplicity of 3. Here, because there's nothing there, is a multiplicity 1. So you add those up. Okay, so if you see this, that means multiplicity 3. And then if you see this, that means a multiplicity 1. So that means the degree of this function is 4. Could you add those together? All right, that's how you determine if it's going to be an even degree or an odd degree when it's in factored form. And then, of course, leading coefficient is whatever the leading coefficient is. You see this is your leading coefficient when it's in factored form. So in this case, that's negative. If you don't see a sign, it's positive. So this is just like a multiplication table. So you start here. If you have an even degree with a positive leading coefficient, then your arrows point like this. Here's your end behavior. Just basically your behavior is always going to be the same for these types of situations. If it's odd, but then you have a positive leading coefficient, then it meets over here into this one, and you see how your arrows point. Okay, so that's just something that you can look at, and just some examples of stuff there. All right, but then let's look at this and put these together. All right, so we're going to literally put all this together. Okay? So when I'm looking at a graph, there's things that I can tell just from looking at the graph. I can tell the roots. If I see it cross the x-axis, I know roots. Now, with the roots, you got to think about how it's crossing through. So this is going straight through. This one is bouncing off. And this one is snaking through, so snakes through. So when I go through these roots, I'm going to put their multiplicities with them. So here, this root is -5, that's the first one. But the multiplicity for that is 1. And then if you don't see a multiplicity written, then it means it's a 1. The next one is -2, but because that bounces off, you have a multiplicity of 2. And then the last one is 1, but because it snakes through, the multiplicity is 3. Now, if you don't see a multiplicity written next to a root, then it's a 1. So leading coefficient, the right side is up, so it's a positive leading coefficient. Okay. Now the factored form for this, remember, if you have your roots, you have the factored form. Okay, we have a positive leading coefficient. We have a root of -5, so it's going to be x plus 5. We have a root of -2, so x plus 2. But because the multiplicity is 2, we got to put that there. And then the last one is x minus 1 because the root is positive 1, but the multiplicity is 3. And then the degree for this is 6 because we add up the multiplicities. Okay, so then your end behavior, as x approaches negative infinity on the left, as x approaches positive infinity on the right, what is your y value doing? And so the right side is pointing up to infinity. The left side, oops, my bad, it's even. The left side is pointing up as well. Remember, if the degree is even, your arrow is pointing in the same direction. Okay, and I can see on the graph here, arrow pointing up, here, arrow pointing up at the end. All right, next one. Okay, I see here, got an arrow pointing up. Here, I got an arrow pointing down. Okay, let's look at the roots. Root, root. Be careful here. The scale for this is a little bit different. Okay, that's a 1 there. This is -6. I think I just covered that up. All right, so roots, -6, multiplicity, let's see. Okay, that's snaking through or twist. Here it bounces. So that's a multiplicity 3 because it snakes. X equals 1 because it bounces is multiplicity 2. So that lets me know right now the degree is 5. So we have an odd degree. So that lets me know the arrows have, that thing there. Now the leading coefficient, because the right side points up, is positive. Okay, so for the factored form, I take my roots, multiplicity 3, x minus 1, multiplicity 2. Remember, factors or roots to factors, you got to change that sign there. Okay, so we got our factored form. All right, so end behavior, as x goes to the left, as x goes to the right. Again, you can put y equals or f of x, it doesn't matter. Y approaches something. Okay, again, leading coefficient is positive, so that means this is going to approach infinity on the right, but because it's an odd degree, the arrow is pointing in opposite directions, so this is going to point to negative infinity. Remember, arrows opposite for this. All right. Okay. All right. So just looking at this is just kind of a graph. These are just a bunch of different graphs, and then just some of the key things that we talked about at the bottom. And you can look through it. And this just talks about the multiplicities. If it's straight through, bounces off, or twists, what the multiplicities are. All right. Last thing. So putting all this together to sketch a graph and to do a bunch of couple other things. So starts off, we look at what we have. So it's telling us the degree. and it's telling us the leading coefficient. So the leading coefficient here is negative. So I know my arrows point down on the right and then up on the left because it's odd. Odd degree, arrows point opposite directions, negative leading coefficient, right side down. Okay. So you notice these are like my little cheat sheet. This just gives me an idea of the arrows. Now for the roots, I have x equals -2, but there's only one of them, so the multiplicity is 1. Here, x equals 1, but it shows up twice. Multiplicity is 2. Okay, so factored form, because I have the roots, I can put them in factored form. The multiplicity, again, is your exponent. Oh, my bad. And then they give us the leading coefficient, so I need to put that in front. So that should be a -2 there. Okay, now, I'll do standard form at the end here. Okay, so in terms of sketching the graph and the end behavior, so because it's an odd degree and the leading coefficient is negative, I know that this is going to point down, but then this is going to point up because of the opposite sides. And then I go to my roots, -2 and +1. And then I sketch the graph from there. So to sketch the graph, I'm going to look at my arrows and use my arrows as a key. This side points up, so I know that this is going to come in like this. This side points down, so I know that this side is going to end up pointing down when I'm done. Okay, so when I sketch it, I'm just going to start on the left-hand side, and then I'm going to approach the first root. Well, the first root has a multiplicity of 1, so it's just going to go straight through it. Nothing funny. Okay, and I'm kind of over-exaggerating this part. So really, it's just going to kind of come down. But then eventually, it's going to have to curve back to approach the next one. But when it approaches the next one, it's going to bounce off of it because of the multiplicity, and then it's going to go back in this direction. And then it just keeps going in that direction. So that's where you see those arrows. Okay? So there's your sketch. Now the standard form, sometimes you won't be asked for it or whatever, but really with standard form, you're literally going to multiply this all out. So to do the standard form, you're going to take it and you're going to multiply it all together. So you're going to say -2 x plus 2 x minus 1 x minus 1. Remember, x minus 1 with a multiplicity of 2 means you have two of them. Okay, so I'm going to sort of do this work in different places. All right, so x minus 1, I'm going to do the x minus 1 first. I'm doing this one time. I'm not going to multiply these out every time. And so I got that. This is going to be x squared minus 2x plus 1. Okay, now once I have those two multiplied together, I got to multiply by x plus 2 now. And so now I'm going to multiply that together. So that's going to be, real quick. All right. So when I multiply this out, that's going to be x to the third, 2x squared, negative 2x squared, negative 4x, and then 1 times x. Let's go over here. That's 1x. 1 times 2 is 2. So when I combine like terms, I get x to the third. Sorry about that, x to the third, negative 2x. Negative 4x plus x is negative 3x plus 2. All right. So my standard form is, oh shoot, my bad, I forgot. And then I'm going to have to take this and multiply everything by -2. So when I did all of these, that's x to the third minus 3x plus 2 when I multiplied all that together. you won't always be asked to do this. I just wanted to show you one time what it means to expand or put it in standard form. So that literally means multiply everything together. Okay, so it can get a little tedious. All right, but that's it for that. Okay, last one. If you want to stop the video here, you can. I'm at 30 minutes, so I think that's long enough. But um, you can stop. I'm gonna do this one real quick, and then you guys can work on the homework. And I'll show you the homework before I end the video. All right, so look at what they give us here. They give us the function. Oops. And so in this function, we can tell a few things. So we have our roots. So we got x equals 1. Now the exponent for that is 1, so it's a multiplicity 1. X equals -3, but the multiplicity is 2. Okay, so adding that together, I know that the degree of this function is 3. So it's odd. Okay, just a bunch of things that I can tell just from that. Okay, the leading coefficient, the value of that is 2, but it's positive. So that automatically lets me know when I sketch this, I got an arrow pointing up on this side, arrow pointing down on this side. Okay, if the degree is odd, the arrows point in opposite directions. Positive leading coefficient tells me that the right side points up. Okay, and then that means because it's odd, automatically the left side goes down. Okay, if it's even, they both point in the same direction. And so looking at the end behavior, so I can go ahead and put that. Right side is up, left side is down. Okay, the domain basically is going to be all real numbers. For all these functions here, the domain is always going to be negative infinity to infinity. The range, if it's an odd, will be negative infinity to infinity as well. If it's even, because they both point in the same directions, your range is going to be different. It's gonna go from a number to infinity, or a number down, or from negative infinity to a number. So it's a little bit different for that. But you're not going to always be asked about the ranges and stuff for these. And so we're going to sketch the graph now. So we're going to take the roots, x equals 1 and x equals -3. 1, 2, 3. Okay. And then we're going to sketch our graph. So this side is going to point down. So I'm going to start with this side. Always start on the left when you sketch, work your way to the right. So when you approach the -3, this is -3 here. The multiplicity is 2, so it has to bounce off. It didn't work out too well. It's going to bounce off of that. It's got to curl back towards the other one, but the other one only has a multiplicity of 1, so it's going to go straight through. And that's your sketch. Okay. Now, for homework, so you're looking at pages 42, 43, and 45. I know you're thinking this is a lot, but it's not. 42, 43, and 45 all just deal with end behavior or something else. And so you're not sketching anything or whatever. You're just using the format to do the end behavior. So the function type, this is linear because it's a degree 1. This is degree 1. Here, this is degree 4. This is I think this is the highest we go, but this is called a quartic. I'll do that one for you. All right, and then end behavior. So degree 1, it's odd. So the arrows point in opposite directions. The leading coefficient is always the leading coefficient for your biggest degree. So really this needs to be written in order. It should be 2x positive 2x plus 3 positive 3. So the leading coefficient is positive. So that lets me know that the right side is pointing up, but because it's an odd function, the left side points down. That's all I'm doing. Okay, number 2, it's a degree 4, so it's even, which means they both point in the same directions. Positive leading coefficient. So that lets me know that this is pointing up, so this will point up. This one's a little weird. This was actually an exponential function. So that one's different, but it's 3 to the x, so it's going to look like this. So with these types of functions, your right side points up though, because it has a leading coefficient. That's that. And then the end behavior for these, because it starts to flatten out, it's actually going to approach 0. Right, as your exponent gets a little bit more negative, it's going to approach 0, and I can show you that more in class. That's all you're trying to do there. Remember, if it's in factored form, you take your multiplicities, you add those together. So here the degree is 2, which means this is a quadratic. And so it's even, which means both arrows point in the same directions, but it has a negative leading coefficient. So that means that this side's going to point down, right side, which means the left side also points down because it's even. Even, they both point in the same directions. So that's what you're doing for these. Okay, and then if it talks about the y-intercept, remember the y-intercept is pretty simple. The y-intercept is when x is 0. So all you're going to do is plug in 0. And if you plug in 0, all the x's are going to go away except for the constant. So that's pretty easy there. All right, I'm done. See y'all tomorrow.